So one of the last parts of this chapter is going to be intermolecular forces. You've done this before, so hopefully it's a review for you and not something new that you're learning. So let's look at this. So first of all, intermolecular forces, short form IMF, and this is not the Mission Impossible thing, but anyway. IMFs or intermolecular forces are the forces between molecules, not within the molecules, but between two molecules. And what these determine is the physical properties of substances. Okay, so the physical properties that we generally deal with in organic chemistry, there are many, of course, but we'll be focusing more on what their melting point, boiling points are, which helps you determine if the substance is going to be a solid, liquid, or a gas. And hopefully you'll be able to predict this at the end of even this PowerPoint. Okay, but eventually as we get on to organic molecules, then hopefully you should be able to predict those kind of things. Okay. Surface tension, I don't expect you to predict those. If you don't want to, that's okay, but I would like you to determine the solubility of substances, okay, in different substances, okay, itself. So viscosity, not so much. These two things are a little bit more on the physics side, although we do deal with surface tension also and viscosity in different ways, not so much in chemistry though, okay, but for us it's really important for us to know the nature, the physical nature of the substance, and then of course the solubility. Those two are key, and then everything else is also important but secondary to that. Okay, so first of all, intermolecular forces, the most important thing is going to be the polarity of the molecule, okay, for us to help us determine what kind of intermolecular force we are going to have. Okay, and these three are the main properties we are going to focus on eventually as time goes on, is the boiling point, melting point, solubility, and vaporization. Vaporization is just how the molecules are leaving the substance, liquid, solid, whatever it is, okay, the vapors that are coming out. So I mean, boiling point is kind of similar, but boiling point is when you actually have the atmospheric pressure equal to vapor pressure. What is vapor pressure? Vapor pressure is the pressure exerted by the vapors of any substance coming out. Okay, so solids, you don't really have that much vapor coming out, but liquids, you have a lot more vapors coming out. Why do we have that? Intermolecular forces. Okay, so let's deal with that first. Okay, so intermolecular forces are going to be in everything, right? In any kind of a compound, you're going to have intermolecular forces. So ionic compounds will have it too. Covalent compounds also will have intermolecular forces. Ionic forces or ionic compounds will have what is called ionic forces. And these are between cations and anions, which are positive and negative. Okay. These positives and negatives are, opposite signs. And because of that, the ionic forces are really, really strong. If they're really, really strong, then they're going to have really high melting points. These molecules will have high melting points. Why? Because it's hard to break those intermolecular forces. That's really what we're dealing with here. Okay, so if you have two molecules, so like, hydrogen interacting with another hydrogen versus HCl interacting with another HCl. This is the intermolecular force. So how hard or how easy it is to break those forces. Okay, so as I'm saying, for ionic compounds, it's the strongest force. Okay, so it's really hard to break that interaction. So that's why ionic compounds are going to have really, really high melting points and boiling points. In covalent compounds, we have three different kinds of forces. So ionic compounds have only one force. Either you can call it the electrostatic force or the ionic force. But covalent compounds are going to have three different forces: dispersion, dipole-dipole, hydrogen bonding. Okay, so three different forces. I've written them in a particular order from lowest to the highest. Okay, which means dispersion forces are the weakest of all intermolecular forces, and hydrogen bonding is the strongest one. Okay, so let's take one at a time. So for dispersion forces, it is the first force we're looking at, or it's called the van der Waals forces or the London forces, whatever you want to call it, it's all the same. So dispersion forces is the weakest dispersion force, okay? So in these kind of molecules, you don't have any kind of polarity, okay, whatsoever. So what they do is they create what is called an induced dipole, okay? And this kind of induced dipole is highly dependent on the size of the molecule. Okay, so there is a size and there is other things also, but electron density is really what we're talking about, because as you change the size, you change the electron density and vice versa. So what does this mean? The best example here, okay, for us to deal with is chlorine, bromine, and iodine, which is the halogens. So going from fluorine to iodine, the atomic size increases. Why does the atomic size increase? Because the number of electrons are also increasing. So remember what I said over here is that this force is entirely dependent on just its own size of the molecule, because there is no polarity. So if you look at fluorine, it's a nonpolar molecule, so is iodine. But what happens is that fluorine and chlorine are both gases, bromine is a liquid, and iodine is a solid. So something is happening, that you're going from gas to liquid to solid. So the only thing that has changed is the size, which changed because of the electron density. Okay, so let's try to understand what's happening over here. When you have such a large size as an iodine, this is iodine, let's say, so it's a huge molecule. This is iodine, like an I2, okay? This dashed line over here, that's the intermolecular force, okay? So this is I2. So because it has such a huge size, and remember, usually the atoms are pretty much empty spaces. The nucleus is the most dense part of the atom or the molecule. So in such a big, huge molecule, the nucleus comes on one side and the electrons come on one side. So which means there is enough space for them to kind of hang by themselves. So here, because the nucleus is on one side, now you have a delta positive side of the molecule and you have a delta negative side of the molecule. This is called induced dipole. The molecule did not do anything special. It just distributed its neutron and, sorry, not neutron, the nucleus and the electrons in two different spots. And so because of that, there is a charge distribution. That charge distribution is enough, okay, to cause another iodine molecule to have interactions with each other, because the other iodine molecule is the same way, right? You have the positive and you have the negative. So the positive and the negative of the two iodines now will start interacting, and that interaction is the dispersion force. So again, there has been no polarity in the molecule. There is no charge in the molecule. It's just a self-induced charge. What happened? The only thing that happened is the size changed, right? Fluorine is a very small atom. So fluorine, even if two combine, it's not going to be able to do this, okay? Bromine can do it, but not as much as iodine. So which means the interaction, this kind of a dipole, induced dipole interaction is way higher for iodine than for bromine, than for chlorine, for fluorine. Okay, and so this induced dipole can happen in any molecule with different sizes. Okay, so it doesn't have to be the same atom also. Okay, so even if you have something very different, as in CH4 versus C4H10, where you have only one carbon versus 4 carbons, this is bigger. Okay, so because the C4H10 is bigger, it's going to have a higher dispersion force. Because it has higher dispersion force, it's going to have an induced dipole. Because it has that, it's going to have a higher boiling point than CH4. Am I asking you what it is? No, I'm just asking you which molecule has higher intermolecular force. That's my question to you usually. Okay, so here, as the size increases of the molecule or of the atom, you're going to get higher interaction, okay, higher intermolecular forces. So here are the properties, okay, for fluorine, chlorine, and iodine, and you can see how the boiling point has changed from going from gas to liquid to solid, and here's the boiling points, okay, for all of this. So here are some examples that I was just talking about also, and this is not for C4, this is just for C2. So even going from 1 carbon to 2 carbons, you have such a huge change for the boiling point, okay, for bigger molecules. So it's a small thing, but it has such a huge effect, you know, that you don't think that just having a larger size is going to change the intermolecular force, but it does change that. Then you can have dispersion forces also in different kinds of chain types. Now, when we get to organic molecules, right now, until now, we've been dealing with smaller molecules and inorganic molecules, very simple. But when we get to organic molecules, not only do you have larger number of carbons, so we talked about methane, which is a very small molecule, 1 carbon, but you can have, you know, many carbons in there. And once you start having many carbons in there, they start forming different structures. Okay, it's like having Lego pieces and those Lego pieces start forming different kinds of shapes, okay, in there. This one is called a straight chain, this is branching, and this one is even more branching, okay. So in these cases, these are all 5 carbon structures, okay, they all have 5 carbons, but their physical properties are different, okay. And you can see here that the straight chain here has the highest boiling point, 36, versus the branched one, which is 9.5, okay, boiling point degrees Celsius. So it's different. So why is it different, okay, for the straight chain versus branching? So you have to think about the interaction that is happening. It's intermolecular force. Intermolecular force means that another molecule has to get close to this molecule in order to have that interaction. Once you start having branching in a molecule, the molecule is almost putting like a stop sign out there. No, don't get any closer, okay? This molecule is open for interaction. So another molecule will come in and there is interaction going on. When you have even more branching, then that kind of branching prevents all these atoms from getting closer to each other. When they're not getting close to each other, they're not having any interaction, so which means there is no intermolecular force. If there is no intermolecular force, boiling point is really weak. Okay, here your intermolecular force is going to be a lot more because there's a lot more atoms to interact with each other, okay, or have those dispersion forces from each other. So straight chain molecules in general are going to have a higher boiling point than branched ones. Dipole moment. So we have talked about dipole moment before, and dipole moment was the motion of any kind of a molecule in electric current. And we've talked about the fact that dipole moment is determined by the difference in the electronegativity and also the shape of the molecule. Okay, so we covered that before. Now we're taking it to the next level, okay, which is the intermolecular force itself. So the higher the dipole moment, the higher the boiling point, okay, of anything. So here I've given you some dipole moments, all right, of molecules. So hydrogen and chlorine we expect 0 because they are the same kind of atoms, which is also called homotopic. So these are the same atoms, and so therefore no dipole moment. But as soon as you start having any other atom, then you will have a dipole moment. Now fluorine is more electronegative than chlorine, so that is why it has a higher dipole moment than HCl. Okay, HF is higher than HCl. So here you can see, you know, how molecules will have different dipole moments. The more the dipole moment, the more the intermolecular force between them. Okay, the higher the intermolecular force, the higher the boiling point or melting point. Okay, those kind of things. So that is how you determine the physical properties of substances. Now I haven't talked about solubility yet. Okay, I will. Right now I'm just focusing on boiling points, and I'm not even doing too much about solid, liquid, or gas because it is still a little bit harder, okay? But try to understand that if you have more interactions, if you have more intermolecular forces, it is going to be harder to separate out the molecules. And if it's harder for you to separate out molecules, then they will go to higher boiling points or turn into solids if they have more interaction, like iodine did. Okay, so here also, once you have, higher intermolecular forces, then you have higher boiling points at least. Okay, coincidentally, these are all liquids and gases. So dipole moment, hopefully it's a little bit easier. To determine the dipole moment, again, you don't need the numbers. You just need to know the difference in electronegativity from the periodic table, the trend, and then the shape of the molecule. Okay, and make sure that it is asymmetric in order for it to have a dipole moment. So here we've gone through this before, so I don't want to do this again. Okay, so how we draw the cross here, remember, so if you have oxygen, which is more electronegative, it will pull towards itself, and that's how you draw the dipole arrow, okay, in there. So if you have something symmetrical like these molecules down here, you will have no dipole moment, okay, in there. And then here are some more examples of some structures, and then also their dipole moment and some physical properties, so you understand how this works. So the higher the dipole moment, the higher the boiling point. Okay, so if you don't want to remember the names, that's fine, don't worry about it, just look at the structures here. So if you look at CH3, CH2, CH3, there's absolutely no electronegative element in there. The whole bonding is non-polar. Now you've increased at least some polarity over here by introducing oxygen. So that will give it some dipole moment. Okay, when you have chlorine, you have even more. And then by the time you get to these two, there is a lot more of dipole moment in there. You should try to draw out the Lewis structures for all of these, okay, in order to understand how this works. So I'll draw out the one for CH3CHO. How is that? Okay, because the other ones, I think I know you can do it, but let me just go ahead and do it for CH3CHO. So CH3, so you start with the one carbon, right? So hydrogen is always going to be terminal atom. You're never going to put that in the middle because it has only one bond. And then you have the other C over here. So the C is bonding with C. So these hydrogens that are written in the middle doesn't mean that you have to put them in the middle. Okay, so you put them like this, and then you have HO, so H and then O, and then you're looking at this hydrogen and this carbon, and hopefully you're freaking out like, oh my God, this has only 3 bonds. So you put double bond here. Okay, and so once you have the double bond here, now everything is octet. So this bond right here is the polar bond. Right, so oxygen is electronegative and then carbon is delta positive. Not only that, if you look at this carbon, this is three electron groups. So if it's 3 electron groups, it's actually AX3, which is trigonal planar. Okay, so here is the oxygen, here is carbon, here is hydrogen. So it really creates a very nice kind of dipole moment, okay, for this molecule. That's why it's a little bit high here. So that's how you work it out. So make sure you write the structures of the others to understand how the dipole moment is working. And finally, hydrogen bonding. I feel hydrogen bonding is kind of simple, but the main thing you need to know from here is the fact that hydrogen has to be attached to fluorine, oxygen, or nitrogen, okay, in order to show hydrogen bonding. So just because HCl has hydrogen in it doesn't mean that it's going to have hydrogen bonding. Hydrogen bonding has to be bonded. The hydrogen has to be bonded to fluorine, oxygen, or nitrogen, okay. So HF, for example, is going to have hydrogen bonding. Then water, of course, is going to have hydrogen bonding. So I've shown you how this works. This is the shape of water, and then hydrogen is bonding with the oxygen. Remember, oxygen is very electronegative, all right? And so is nitrogen, and definitely so is fluorine. So that's why these 3 atoms are very different, very electronegative. And if you bond hydrogen to them, then they will cause this kind of a bond. This bond, hydrogen bond, is almost the same strength as a covalent bond, which is a very strong bond, okay? Water has a boiling point of 100 degrees Celsius, right? We know that already. So why is it so high? Because of hydrogen bonding. Okay, so these are very strong bonds. Our DNA is held together by hydrogen bonding, so we know it's a very strong bond. Here is an example for ammonia. Okay, so comparison for the intermolecular forces, definitely hydrogen bonding is strongest. Dispersion is the weakest one. Okay, and for us we need all of these three to understand the physical properties in organic molecules. Okay, so here if we look at this problem, what are the two key intermolecular forces here? I know the answers are already given here to you. They're not kind of just appearing because for me it's very distracting to do that. So I just leave, most of the time I just leave it there. But anyhow, so here we have a chlorine. So we are going to have a dipole interaction over here. Here we have an oxygen attached to the hydrogen. So we are going to have hydrogen bonding also. Okay. Now, if you're wondering, well, I will also have dispersion. Yes, you will. Okay. So whenever you are asked a question about intermolecular forces, you should pick only the highest one, unless there is another one that is highest or the second highest, which here in this case is dipole-dipole. Okay, dispersion forces you're going to find in pretty much every molecule, so why even bother writing dispersion forces? The only time you should be focused on dispersion forces is when you have something that is completely nonpolar and or different size. That's when you should focus on dispersion. Okay, otherwise don't even bother writing dispersion forces. Okay, so what are the intermolecular forces between the molecules given in the table? So here we have CHCl3. So if you want, you can draw out the structures for this, and I really encourage you to do that. But I'm going to go through it without drawing the structures. Okay, so here I know that this is CHCl3. So this is like X, right? AX4. If it is AX4, then I know it's a tetrahedral. So which means that the chlorine here is not exactly symmetrical. Okay, let me go ahead and draw that out. I cannot resist it. So Cl, Cl, Cl. So here, because of Cl, Cl, you have three chlorines over here. This is the right structure also for it, shape also for it. So here you have the dipole-dipole, okay, interaction. Now, dispersion force, generally it's not going to be that much, okay, for it. So if you're asked for, you can give up to 2, but generally just leave up to 1. So I think I'm going to cross that out, okay. So dipole-dipole forces are really the more important one here. Br2, there is absolutely no other atom in there, so it has to be only dispersion force. You cannot say that there is no intermolecular force, by the way. Okay, that's not a good answer. So you have to give some intermolecular force. Okay, and so dispersion force is the weakest one here. So that's the one that's going to be for bromine. Now, calcium nitrate here. Calcium is a metal. As soon as I know it's a metal, I know it's going to be electrostatic force. That's it. Okay, case closed. Now for this one here, CH3OH, I can see the OH here. As soon as I see the OH, I know it's hydrogen bonding. Okay, so try to keep it simple as you know what I did here, and I know it might seem simple, but it's going to be simple, definitely. Okay, it's not going to be that hard. Okay, and then here, which one of the following has the highest dispersion force? I'm not even asking you for anything else. So what are you looking for in dispersion force? Size, right? So the largest one is going to have the highest dispersion force. That's it. Okay, so arrange the following molecules in increasing order of boiling points. Okay, so we took the same once again. So CHCl3, we have that in the previous slide. So here we're just going to arrange them in boiling points. So electrostatic force is the strongest force. Okay, so that's going to be the highest one, followed by the hydrogen bonding, followed by the dipole-dipole, followed by dispersion. Dispersion is the least. Okay, so electrostatic force followed by the hydrogen bonding, followed by dipole, followed by dispersion. So this is going to be the highest boiling point or melting point, and this is going to be the lowest. Bromine is going to be the lowest. Okay. Now, here is an example for solubility. So I haven't talked about solubility at all, but I want you to remember this rule here. Like dissolves like. So when we say like dissolves like, you need to know at least one of the likes, right? What is this about? So what it means is that when you look at any molecule, you need to figure out what are the intermolecular forces in there. So this problem that we did before is to help you with this, okay? Because to determine the solubility, you need to know what intermolecular forces you're dealing with. So what's the question here? Which of the following molecules will be more soluble in water and which is going to be in hexane? So hexane, the structure is given to you here, the molecular formula, and which will be more soluble in water. So what is water? What kind of forces does water have? Water has hydrogen bonding, okay? Hexane, looking at it like this, completely nonpolar, which means it has dispersion forces. Okay, so which means we're dealing with two different kinds of forces here. We are dealing with hydrogen bonding and we are dealing with dispersion forces. Now all you have to do is go through these and figure out the intermolecular forces. So we know already for C4H10, have we done this before? No, not really, but we'll do it anyway. So C4H10 is simply non-polar. You don't have any polarity in there. So if it's completely non-polar, it has dispersion forces. C6H14 also has dispersion forces. So like dissolves like. So which means these two are going to be soluble. C4H10 will not be soluble in water because water has really high intermolecular forces, the hydrogen bonding. So it's not going to be soluble there. CH3OH here has hydrogen bonding. Hydrogen bonding will be soluble in hydrogen bonding, not in the dispersion forces. It is really that much, okay? It literally is that much, okay? How do you see that? When something dissolves in something, you cannot tell that unless there are different colors, okay, or something like that. But when you dissolve, let's say you dissolve sugar in water, you cannot tell just by looking that the sugar is dissolved in water because they're completely dissolved. Okay, so what happens in solubility is that you're not able to tell them apart. So when you mix C6H14 with C4H10, they mix so well that it just looks like one substance. Okay, when you mix CH3OH with water, it should look like one substance. It does. When you mix C4H10 with water, it's not going to mix. Like they say, oil and water. Okay, that's what it's going to be like. So two different phases. You'll be able to see, I shouldn't say two phases because both are liquids, but you'll be able to see two layers. Okay, you'll see two liquids there because they're not dissolving. All right, the last one, calcium nitrate, has ionic forces. Now, ionic forces are a little bit different in the sense that they don't match with any one of these, right? So ionic forces generally will dissolve in the highest intermolecular force, which is then hydrogen bonding, and which is also not for all though, okay? So water will dissolve calcium nitrate, all right, because of hydrogen bonding and dipole-dipole forces. I will say one thing, that water is the universal solvent, as we all know. Without water, there is no life. All old civilizations, they lived near water. They all started near water. So water is a little bit different kind of a thing. If you look at this molecule here, I'm just going through a sidetrack here. This is CH3OH. This also has hydrogen bonding. B and C will not dissolve though. So even though water has hydrogen bonding, it is dissolving calcium nitrate. But CH3OH will not dissolve calcium nitrate. Okay, so it is not, how should I explain this? Okay, this has the hydrogen bonding, but the dispersion forces are also there. Okay, so just because you have hydrogen bonding does not mean that you'll dissolve all salts. Water is just a little bit different. Okay, the hydrogen bonding here is quite different. Not only it has hydrogen bonding, it has the dipole-dipole forces as well. It has absolutely no dispersion forces. So water will dissolve anything that is electrostatic force. Okay, but these two will not dissolve. So it's, you know, you learn this as you go on slowly and slowly, and you figure it out. Okay, I think that's pretty much it for yeah. Okay, alrighty then. I hope it was good.